Alright guys, happy Monday. So in this video we are going to be looking at solving trig equations using the identities that we have previously looked at, specifically the double and half angle formulas. As you can see, I have 3 examples here that I'm going to get to, all of which are going to be using those identities that we used previously. Keep in mind, when you're solving trig equations, you don't have to use these identities. And also there's many other identities that we have learned and we will learn that you will need to be able to use in trig equations. So just keep that in mind. We're focusing on the double and half angle formulas. Before we get started, don't forget that in the Larson textbook, page 457 to 466, he's going to go ahead and address this topic as well, potentially in a different way, so it might be worth looking at. And without further ado, let's go ahead and get started. Question number 1. Real quick though, before we get started, feel free to do these 3 problems before I attempt them, and you can check your answers with mine. We may solve them the same way, we may solve them in different ways, and I think there's a lot of value in that. So try these problems before I go through the answers, but let's go ahead and get started. Alright, so let me go ahead and get number 1 written on a new screen. We have here cosine 2x is equal to cosine x. Alright, so one way to solve this is to just look at the graphs and see when they intersect, but that is not the goal here. Our goal here is to solve these algebraically. We'll look at a graph at the end and see if our answers are in fact correct. So cosine 2x, there's many different formulas for cosine 2x. We got cosine squared x minus sine squared x. We have 2 cosine squared x minus 1, and we have 1 minus 2 sine squared x. And so we have 1, 2, 3 possibilities here, and I think the best one is number 2. Because if we use this one, we have a problem with just cosine x in it. We have a cosine squared x, a cosine x. If we use 1 or 3, we'll be having to deal with some sine squared x. And then that will involve the Pythagorean identity, which will take us to number 2 anyways. So let's go ahead and turn cosine 2x into equation number 2. So 2 cosine squared x minus 1 is equal to cosine x, and now we are in familiarity land. We know how to deal with this. Let's go ahead and move everything to one side. Minus cosine x minus 1 is equal to 0, and here we have a quadratic. All right, so we got 2 cosine squared x minus cosine x minus 1, so that's going to be... Oh, there's only one possibility, so 1 times 1, 2, 1, 2, 1, 1, 1. That is going to be 2. And I'm just doing a lot of thinking in my head. Plus 1. And cosine x minus 1. Cool. Let me double check that that's right. All right, factoring can be difficult, but checking your answer is not. 2 cosine x times cosine x, that's 2 cosine x squared. 1 times negative 1, that's negative 1. And we have a we have a negative 2 cosine x and a positive 1 cosine x. That sums to negative 1. Perfect. Cool. So we now have zero product property. Right, this thing can either be 0 or this object can be 0. Right, so we just need to solve these 2 things. Let's do that on the next page. Alright, so I'm just going to go ahead and grab the 2 equations. Jump to the next page, and there it is. Sweet. So we just need to solve these 2 things. Not too bad. Right, so 2 cosine x minus 1 equals 0. That's going to be cosine x equals negative 1/2. Cosine is negative 1/2 when the x coordinate is negative 1/2, so that's going to be here and here. That's going to be at, what is that, 2 pi over 3 and 4 pi over 3. So we got, let's just do plus or minus 2 pi over 3. So x can be plus or minus 2 pi over 3 plus 2 pi k. Cool. And then over here we got cosine x equals 1. That happens one time every period. That happens at, oh, that's nice, 0 plus 2 pi k, or better known as just 2 pi k. Awesome. There are our solutions. Let's go ahead and look at the graphical solutions and see if they agree with our algebraic solutions. Just go ahead and pull up Desmos. There we are. Let's go ahead and write cosine 2x. There's cosine 2x. Let me go ahead and zoom on in. And let's go ahead and add cosine x. And let's see, we are intersecting at 2 pi over 3, 4 pi over 3, or aka negative 2 pi over 3 plus 2 pi k, 2 pi, and 2 pi and 0, 2 pi k. So this does in fact agree with our solution set that we figured out algebraically. So we know that this answer is correct. One other thing I wanted to say is, in doing this problem, we never squared anything. So there is no reason for us to double check our solutions at the end. There are no extraneous solutions. Yay. If we had squared at some point, we would have had to check, but we never did that here. So that's one nice aspect of using identities. Cool. All right, let's go and look at the next problem, problem number 2. All right, so let me go ahead and grab number 2. There we go. Awesome. Let's go ahead and track that up. All right, so we're looking at sine squared x plus 2 is equal to 2 cosine squared x divided by 2. So we have some identities here, the Pythagorean identities, but what I want to focus on is cosine squared x divided by 2. That thing is screaming, use an identity on me. Use one of the formulas that we talked about last time. So cosine squared x divided by 2, let's remind ourselves what the half angle formula for cosine is. Cosine x divided by 2, that's going to be the plus or minus the square root of 1 plus cosine x all divided by 2. But we are looking at the square of cosine. So what I really care about is, let's throw square there. Let's throw square there, and we got cosine squared x divided by 2 is equal to 1 plus cosine x divided by 2. The plus or minus goes away. I'm killing it with the square. And what I really want is the square. So this is the formula that I care about. I can go ahead and substitute it right into there. We got sine squared x plus 2 is equal to, and what's really nice is this 2 right here is going to cancel with this 2 right here. So cosine squared x divided by 2, that's just going to be 1 plus cosine x. That's really nice. All right, so we've done this before. This is just, solving trig equations that we've done in the past. So how do we deal with this? Well, we have a sine function and a cosine function in the same equation. Let's go ahead and change what we can. So we cannot change this at all, but we can change this guy, 1 minus cosine squared x. That is a Pythagorean identity. We got unit circle, we got cosine x, we got sine x. Cosine squared x plus sine squared x equals 1. So 1 minus cosine squared x is equal to sine squared x. Let's go ahead and continue. We're here. Let's go ahead and move everything to one side because this is screaming quadratic. So we got, let's see, move everything on this side to the other side. So 0, we're going to have a minus 1 minus 2 minus 1. That's going to be a minus 2. We're still going to have a plus cosine x. And we're going to have a positive cosine squared. Cool. So we got cosine squared plus cosine x minus 2 is equal to 0. This thing, hopefully, is going to factor. So I'm thinking u squared plus u minus 2. Two things that multiply with negative 2 that add to 1. That's going to be negative 1 and 2. So I'm going to have a plus 2 and a minus 1. Sorry, I'm just thinking about factoring, thinking out loud. Cosine x, cosine x. And we just need to solve this using the zero product property. So cosine x is equal to negative 2, and cosine x minus 1 is equal to 0. So cosine x is equal to 1. All right. I'm going to go ahead and grab a new page just for the room. So we got cosine x is equal to negative 2, and cosine x is equal to 1. Cosine x equals negative 2. Here's a little picture of cosine. Whee! Little roller coaster. This is never negative 2. So this equation right here doesn't even matter. Cool. Over here, though, cosine x does equal 1, and cosine equals 1 at 2 pi, and any multiple of that, 2 pi k. So there is our solution to this equation. Let's look at a graph of it. All right, so let's pull up Desmos. This is the previous problem. Let's go ahead and get rid of that. We want sine squared x plus 2. And we want on the right hand side 2 cosine squared x divided by 2. All right, so look at that. They are meeting at every 2 pi. There we go. Our solution's correct. And it's a little pretty picture for you. Cool. All right. That's number 2. Let's go ahead and look at our final one, number 3. All right. Number 3. All right, so let me go ahead and grab number 3. There we are. Okay, sweet. So let's go ahead and get started on this one. So I'm looking at this one, and it's screaming quadratic. All right, we got this fourth here. We got some double angle stuff going on. I think I want to approach this one first by getting rid of all of this 3x and 6x stuff. Let's go ahead and make u 3x to make this a little bit more pleasant to look at. So what do we got here? We got 8 sine to the 4th. 3x, I just called 3xu, so I'm going to go ahead and just write u there. We got plus 5 cosine 6x. That is, if I multiply this equation by 2, I get 2u is equal to 6x. So I can go ahead and replace 6x with 2u, and then I got the minus 2 and the 0. Cool. All right, so what else can I do here to clean this up? Let's go ahead and use the identity now. We got cosine 2u, which we need to choose which of the 3 identities we want to use. And because I got the sine over here, I'm going to use the one with sine in it. So cosine 2u is going to be equal to 1 minus 2 sine u. Awesome. So sine squared u, sorry. All right, so let's go ahead and plug this back in. We got a new equation here with equivalent solutions. 8 sine to the 4th u plus 5 times 1 minus 2 sine squared u minus 2 is equal to 0. Okay, cool. Let's continue to clean this thing up. So we got an 8 sine to the 4th u. I'm not going to mess around there, but I will simplify this second expression. Plus 5 times 1, that's 5, minus 2, that's going to be plus 3. And then we got 5 times negative 2 sine squared u. So that's going to be, what is that, a negative 10 sine squared u. All right, so plus negative 10. Sorry about that. Cool. All right, so I could factor here, but just to make it a little bit more obvious, I'm going to do another iteration of substitution. So let's go ahead and call sine squared u. Let's call that, let's go ahead and call that, I don't know, v. All right, so we got sine squared u is equal to v. So 8 sine to the 4th u, that's v squared, minus 10v plus 3 is equal to 0. And now it's become a factoring problem. Let's go ahead and do it. So let's see, we got 8, so 1 and 8, 2 and 4. Over here we got 1 and 3, 3 and 1. So 1 and 3, 1 and 8, that's going to be 8 and 3, that is 11. That's not going to be what we want. 2 and 3, that's 6, 4 and 1, that's 4. That's what we want. 6 and 4 gives you 10. So let's see, we got 2v, we got 4v, and then we got 2, the 1 goes with the 2, and the 3 goes with the 4, and then all we got to do is figure out our sign. So it's either going to be, because this is a plus, minus and minus, or plus and plus, but because that's a minus, it's going to be a minus and a minus. So there is our factored quadratic. Let's go ahead and take this to the next page. That way I have a little bit more room to finish up this problem. There's still a fair amount left to do. All right. So we got 2v minus 1. We got 4v minus 3. Cool. All right, so let's set this equal to 0. So 2v minus 1 is equal to 0. And 4v minus 3 is equal to 0. And then go ahead and add 1 on both sides, divide by 2, 1/2, and over here we got v is equal to 3/4. And then let's go ahead and backtrack. So v, what was v? Let me jump back. V was sine squared u. So sine squared u is equal to 1/2. We want to solve for u now. All right, so sine squared u, square root both sides. And this is the sneaky part, because when I square root both sides here, I get plus or minus the square root of 1/2, which is the square root of 2/2. And over here, I get plus or minus the square root of 3 all over 2. So there's going to be a lot of solutions here. This solution set's pretty large. All right, let's jump to the next page. So we got, I'm going to go ahead and switch back over to the color white. So we got sine of u is equal to plus or minus the square root of 2. And we have, I'm going to write over here, sine of u is equal to plus or minus the square root of 3/2. All right, what was u? Let me jump back. Well, actually, no, let's go ahead and solve this first. Let's solve for u. So u, there's a pretty large solution set here. When is u positive or negative root 2/2? That's going to be pi/4. 3 pi/4, 5 pi/4, and 7 pi/4. So basically, let's just do this. Plus or minus pi/4 and plus or minus 3 pi/4. Right, that's going to cover all bases. Positive pi/4, negative pi/4, positive 3 pi/4, negative 3 pi/4. All right, so cool. Over here, I'm going to have a similar situation. When is sine u plus or minus root 3/2? That's going to be up here at pi/3, 2 pi/3, 4 pi/3, and 5 pi/3. But we got the y coordinate is root 3/2. But let's go ahead and write that in a clever way as well. Plus or minus pi over 3 and plus or minus 2 pi over 3. Cool. All right. Pi over 3, 2 pi over 3, negative pi over 3, negative 2 pi over 3. A little sloppy there. Sorry about that. All right, I am forgetting something, though. Let me go ahead and highlight this in green. I have forgotten my plus 2 pi k on every single one of these. All right, I'm looking for all solutions, not just the solutions between negative 2 pi over negative 2 pi and 2 pi. Cool. All right, so what is u? Now it's time to backtrack with the u. So if I jump back to here, u was 3x. So let's go ahead and write 3x there. So 3x is equal to plus or minus pi over 4, plus or minus 3 pi over 4. All right, let me not forget my 2 pi k. And 3x is equal to plus or minus pi over 3 plus 2 pi k and plus or minus 2 pi over 3 plus 2 pi k. Cool. All right, I'm going to go ahead and grab this, take it to the next page with me. All right, I believe this is going to be the last page for this problem. All right, so we want x and we have 3x. So let's just divide everything by 3. All right, so that thing gets divided by 3 plus or minus pi over 12 plus, let's not forget to also divide the 2 pi k by 3. Right? And then we have 3 pi over 4 divided by 3, that's just pi over 4. So plus or minus pi over 4 plus 2/3 pi k. Right, that's one of our solution sets. And then over here, our final set of 4 sets of solutions. We got plus or minus pi over 12 plus 2 pi over, no, sorry, not 12, I was confusing myself. Pi over 9. Pi over 3 divided by 3, that's pi over 9. Plus 2 pi over 3k. And plus or minus, what is this going to be? This is going to be 2 pi over 9. Plus 2 pi over 3k. And there are our 1, 2, 3, 4, 5, 6, 7, 8 solutions. Solution sets, because each of those has a plus 2 pi over 3k. All right, let me just double check that my answers are right. We got 2 pi over 9. We got pi over 4 plus 2 pi over 3, pi over 12. All right, yeah, there we go. That is it. Beautiful. Cool. All right, so there's your solution set to number 3. Go ahead and check your answer if you did it prior to me doing it. And yeah, I'll go ahead and recap what we did today. Actually, before I do the recap, I just wanted to say that your answers may look different than mine, but they might actually be the same. So go ahead and actually plug into a calculator your answers and then compare them against mine if you have something that's different. All right, so this is what we did today. We looked at 3 different trig equations. We had cosine 2x equals cosine x. We had a trig equation that involved a half angle formula, and we had one that involved a double angle formula. Number 1 wasn't that bad. We just used the identity, turned it into a quadratic, factored, and solved. We did not have to check for extraneous solutions because we never did any squaring, and that's the only dangerous algebra move that we are dealing with at the moment. In number 2, we used the half angle formula, and it kind of actually worked really nicely with this equation. It's almost as if I chose this question on purpose, so it would work nicely. Cool. And then this final one was a doozy, but we used a lot of u substitution to make it more manageable, and we got a huge solution set. So here's solving trig equations with identities. Not too much different than what we did when we were just solving trig equations before, but this just adds another dimension to the set of equations that you are now able to solve. I'll see you guys in the next lesson that involves identities, proving identities using our newfound formulas. So, without further ado, I will see you guys over there.